Hello everyone, welcome to my differential equation class. Today we are starting a new chapter, chapter 7, the Laplace transform. Let me give you a quick preview of the chapter. The Laplace transform is a widely used integral transform which was named after the French mathematician Pierre-Simon Laplace. The Laplace transform converts a function of time t to a function of frequency s. The Laplace transform is useful in differential equation as it converts differential equations to algebraic equations in the S domain. So some problem which should be difficult to solve in time domain becomes easy to solve in the frequency domain. In addition, it applies to general signals in control systems and is useful in dealing with discontinuous forcing functions. Okay, in this lecture, I will define the Laplace transform and its inverse, state some of its properties, and compute the Laplace transform of some basic functions. I will provide you a Laplace transform table at the end, which is a formula sheet for the Laplace transforms problems, and finally show you an example on how to use Laplace transform to solve the differential equations. So let's start with the definition of Laplace transform. We denote the Laplace transform by curve L. So the Laplace transform of a function little ft, where t often represents a time, is denoted and defined by Laplace transform of little ft. It's defined as improper integrals, integral over 0 to infinity, and the exponential term e to the power negative st times ft times dt. Whatever functions we are finding Laplace transform, just put here and we multiply that function by this exponentially decaying functions. And then after we evaluate these improper integrals, this turns out to be a function of s, so we denote by capital F of s. So the Laplace transform of little ft is capital F of s. So small comment here, this multiplier e to the power negative st for s positive is 1 for t equals to 0 and decreases to 0 for t goes to infinity. And we write little ft is a L inverse, means the inverse Laplace transform of capital F of s, and we call little ft the inverse Laplace transform of the transform function capital F of s. And also the corresponding pairs little ft and capital F of s is called a transform pair. So this transform pair means little ft is the inverse Laplace transform of capital F of s, and capital F of s is the Laplace transform of little ft. So let me visualize here. So this is the Laplace transform. It takes the function of time and lands on a transform domain or the frequency domain, and the inverse Laplace transform carries the frequency and lands in the time domain. So the Laplace transform takes the differential equations and gives us the algebraic equations in frequency domain or in transform domain. Okay, so some side notes. The capital F, which is the Laplace transform of little f, the capital F, to exist the improper integrals on the definition of our right hand side of the equation star, which is improper integral 0 to infinity e to the negative st times ft times dt, which is defined by this way or compute by this way, limit b goes to infinity, integral over 0 to b e to the negative st times ft dt must converge. 2. Lowercase letter denotes the signal in the time domain, and uppercase letter denotes its Laplace transform in the frequency domain. For differential equations, the Laplace transform of time derivative contains a term that include initial conditions. For example, Laplace transform of first derivative, little y prime t equals to s times Laplace transform of y minus y0. This y0 is initial conditions. Point number 4, Laplace transform and its inverse are linear operators. The linearity condition is, they both satisfy the linearity conditions. Point 5, computing Laplace transforms can be a little messy sometimes. Just a warning. 6, most of Laplace transform have Koshal form. So to compute the inverse Laplace transform, the main techniques are algebraic manipulations, compute the square, partial fraction expansion, and Laplace transform table lookup. So we study the inverse Laplace transform in our next lecture. Okay, so now let's compute the Laplace transform of some basic functions. So first example, let's compute the Laplace transform of t. Solution. Let's start with the definition of the Laplace transform. So the Laplace transform of t is defined as improper integrals, integral over 0 to infinity, and then the multiplier term is e to the power negative st times whatever function is on the left side. We need to multiply here with e to the power negative st. So 0 to infinity e to the negative st times t times dt. Now it's an improper integrals, so I need to introduce the limit to evaluate this improper integrals. So let's replace infinity by b and take the limit of b goes to infinity, and then t times e to the power negative st dt. Now this integral is a good candidate for the integration by parts. So integration by parts formula is given here. So on this formula, let's assume your t is u and e to the power negative st dt is dv. So then extract the v by integrating e to the negative st dt with respect to t. So negative s is a constant. So the integral of e to the power negative st becomes itself and divided by the constant negative s. So now we have u, we have v. Now we can use this formula. So in the next step, let's copy the limit b goes to infinity. Then u is t, v is e to the power negative st over negative s. Then put the limit t equals to 0 to b, and then this minus from formula, and then integrals, and v du. V is e to the power negative st over negative s dt. And we assume s is positive. So in the next step, put the limit t equals to b and take the limit b goes to infinity. So this term disappears. And when t equals to 0, you multiply by 0, again this term disappears. So the first term disappears. So let's put the second terms. So this minus times minus is plus, so 1 over s. I still copy the limit, and 0 to b e to the power negative st dt. So the next step, let's pull the 1 over s, which is a constant for b limit, so pull outside and put limit b tends to infinity here, so 0 to infinity e to the power negative st dt. Then this integral over 0 to infinity e to the power negative st times dt is a Laplace transform of 1 by definitions, and the Laplace transform of 1 is 1 over s. And trust me, I will compute the Laplace transform of 1 in second example. So then this integral becomes 1 over s, I just copied here, times, this is the Laplace transform of 1, which is 1 over s. Then we multiply 1 over s and 1 over s Now it becomes 1 over s square. So now we found Laplace transform of t is 1 over s square. That is, t and 1 over s square are transform pair. Great. This one we can write 1 factorial over s square. So then similarly we can find out Laplace transform of t squared is 2 factorial over s cubed. Laplace transform of t cubed is 3 factorial over s to the power 4, and so on. Next, let's compute the Laplace transform of exponential functions. So in example 2, Laplace transform of e to the power at, a is any constant. So then use the definition of Laplace transform. So the Laplace transform of e to the power at equals to improper integral 0 to infinity, and then the multiplier is e to the power negative st times this function itself times dt. Then I need to multiply these two functions. So with the laws of index, the same base, then I can add the exponent. So the improper integral 0 to infinity e to the power negative s minus a, I t factor out. So e to the power negative s minus a times t and dt. And this integral is over t, so this s minus a term is a constant. Now I'm using shorthand notations without introducing the limit for these improper integrals. I'm just computing here. So the integral of e to the power negative s minus a times t with respect to dt is itself, and I need to divide by the constant, which is negative s minus a. And I assume s minus a is positive, so s is greater than a. And put the upper limit when t equals to infinity. So this term is 0. So then 0, and then minus from formula, and this minus is plus. Put t equals to 0, e to the power 0 is 1 over s minus a. Great. So we found Laplace transform of e to the at is 1 over s minus a. So as a special case, if a is 0, this a is arbitrary constant. So let's put a equals to 0. Then e to the 0 is 1. Then its Laplace transform of 1 becomes 1 over s. Great. So as promised before in example 1, we found the Laplace transform of 1 is 1 over s. Let's do a quick example. The Laplace transform of 6. So by the linearity, I can pull the 6 outside from the Laplace transform and compute the Laplace transform of 1, which is 1 over s, and multiply by 6, so it's 6 over s. Similarly, the Laplace transform of exponential function e to the power 7t equals to 1 over s minus 7. So I'm just replacing a by 7 in this formula. So this becomes e to the 7t, and 1 over s minus 7 is a transform pair. Great. So now let's keep on continuing. Let's do another example, example 3 now. So let's compute the Laplace transform of 6 plus 5t plus 3 times e to the 7t. Great. So let me take a moment to talk about my numbers 3 and 5. They look similar but not. They are different. This 5 is my fancy 5 with cowboy hat. Haha. So let's use linearity property. So the Laplace transform I can send inside to each of the terms. So Laplace transform of 6 plus Laplace transform of 5t plus Laplace transform of 3 times e to the power 7t. Awesome. So then the next step, Laplace transform of 6 is 6 over s. We already computed here. And Laplace transform of 5t. So I can put the 5 outside and compute the Laplace transform of t, which is 1 over s square. So multiply by 5. so it becomes 5 over s square. Similarly, I can put the 3 outside the Laplace transform and compute the Laplace transform of e to the power 7 times t, which is 1 over s minus 7, and multiply by 3, so it becomes 3 over s minus 7. Great. Now I have a good news for you. You don't need to compute the Laplace transform of the functions using these improper integrals. The Laplace transform table will be provided to you. I'll also provide this Laplace transform table on the exam and quizzes. So let me talk about this Laplace transform table. So the left side is given a function of t, and the right side is given a function of s. So when you apply the Laplace transform to left side, then this gives us the corresponding right side. For example, Laplace transform of 1 becomes 1 over s. Laplace transform of t is 1 over s square. Laplace transform of, let's say, the fourth one, e to the at, is 1 over s minus a. I think we found first 1, 2, 3, 4 formula. Great. And one more comment. I also put this numbering here. I use those numbering when I solve the problem so that you can find easily which formula I am applying on that particular examples. So this formula covers the Laplace transform of trigonometric functions, sine functions, hyperbolic functions, Laplace transform of the derivatives. Let me go over this formula number 58. The Laplace transform of little f prime t becomes s times capital F of s minus f0. If you replace this little f prime by little y prime t, then the Laplace transform of little y prime t is s times capital Y of s minus y0. Great. Similarly, we have a Laplace transform of step functions, Laplace transform of convolutions, Laplace transform of Dirac delta functions, and so on. So this table is important. So please make sure you carry this Laplace transform all the way when you are doing the examples, and carry this one in your classroom also. By the way, this is not a complete list of Laplace transform. Now, before concluding these sections, I would like to show you an example how we use a Laplace transform to solve the differential equations. Okay, so I only give you a definition of inverse Laplace transform. I will cover details of inverse Laplace transform in the next lecture. So just here I'll give you an idea, or just as a warm-up for you to show how the Laplace transform is used to solve the differential equations. I'll do example 4. Okay, so the questions you may ask yourself: how to solve the differential equations using Laplace transform. So the ideas here. So first, the given differential equations, take the Laplace transform of both sides. Idea number 2, apply the rules for derivatives, either first derivatives or second derivatives, and plug into initial conditions. Then your differential equations turns to algebraic equations. Then your algebraic equations is the equations in frequency domain, which has the variable s. Then solve that algebraic equations for the transform variables capital Y of s, which is the Laplace transform of y of t, little yt, and then find the solution in s variables, and look up the Laplace transform table and write the solution as in little yt. So we are making a small loop here. The question is given in the time domain, and we use the Laplace transform to go to the frequency domain. We solve the equation in the frequency domain, which we call algebraic equation. So we solve the algebraic equations in the frequency domain, and we use the Laplace transform table to come back to the time domain. So our answer is in the form of little yt. Hopefully it makes sense to you. So let's do an example 4. So it clarifies these steps. So the question is, solve the initial value problems. So it's a first order linear differential equations with constant coefficients with initial conditions. So y prime, this derivative is with respect to time t. So y prime minus y equals to 1 with initial condition y 0 equals to 0. So the solutions. Step first, which I mentioned above. So take Laplace transform. Let me scroll down. So take Laplace transform of both sides of the given differential equations. So the Laplace transform of y prime minus y equals to Laplace transform of y1, which is on the right side. Then we know this Laplace transform is linear operator, so I can distribute this this Laplace transform inside. So then I can write down the next step, Laplace transform of y prime minus Laplace transform of y equals to Laplace transform of 1. Then apply the rules. So for the y prime, we use the formula number 58 that we talked before, the first derivatives, which becomes s times the capital Y of s minus y0 minus Laplace transform of y becomes capital Y of s equals to Laplace transform of 1 becomes 1 over s. So let's use the initial conditions next. So y0 is given 0, y0 is given 0 here, so I put it back there. Then next step, let me factor the capital Y of s out. So the s left minus 1 left equals to, on my right side, 1 over s. So now this is the algebraic equations in s variables. So let's solve for capital Y of s. So then divide both sides by s minus 1. So then in the next step, capital Y of s equals to 1 over s times s minus 1. So then I need to apply the partial fractions to convert these fractions or this quotient form into a sum of other fractions or difference of other fractions. So I do have both in the denominators linear factors. So this equals to, on the partial fraction expansion method, I can rewrite this equals to a over 1 factor plus b over another factor. A and b are both constant to be determined. But in this example, just by observations, this a turned out to be 1, b turned out to be negative 1. We can check quickly. So check quickly here. So you multiply s times 1, you multiply s minus 1 to this numerator, then this minus distribute minus s, this cancel to this s, and you have minus 1 times minus is plus 1, which is there. Great. So what do we have? We have capital Y of s equals to, on my right side, 1 over s minus 1 minus 1 over s. Then the fourth step says look up the Laplace transform table. So let's concentrate on the right side of this last equation. So look for a functions yt whose Laplace transform is the right side. So we know by looking at the table, the Laplace transform of e to the t power or exponential t e to the t is 1 over s minus 1, and we know the Laplace transform of 1 is 1 over s. So we can rewrite 1 over s minus 1 equals to Laplace transform of e to the t minus 1 over s equals to Laplace transform of 1, and we know L is linear operator, or the Laplace transform is linear operator, so we can pull outside. So what left inside? Only e to the power t minus 1. And by the way, on my left side is the capital Y of s, which is the Laplace transform of yt. So then from the first and the last equation here, we have Laplace transform of yt to the left side, and then the right side Laplace transform of e to the t minus 1. So then finally we cancel that linear operator, so we got yt equals to e to the t minus 1. So now this solution is in the time domain. So this gives us the solution of given initial value problems. Great. So we end this section. So the next sections I will cover the inverse Laplace transform. So thank you.